here we're going to be learning about symmetry. So we're going to be talking about two different types of symmetry, reflectional symmetry and rotational symmetry. And the idea is really the same, that after a reflection or after a rotation, the figure looks exactly the same as it did before the reflection or rotation. So a figure has reflectional symmetry if the pre-image, missed the A, and the image are the same after the reflection. Each point has a matching point on the other side of the line of reflection. Line of reflection can also be called an axis of symmetry. So in each of these four, we're trying to pick out all of our lines of symmetry that we could draw. So we're trying to imagine how we can draw a line and have the image reflect over that line and appear exactly the same after the reflection. So we could draw a vertical line here, because you can see that each of these points, that point has an opposite point on the other side, that point has an opposite point on the other side, so you can flip it over that vertical line and it appears exactly the same on the other side. You could also draw a horizontal one. You can see the same thing is true, there to there, there to there, that top corner down to the bottom corner. They have a matching point on the opposite side there. You might be thinking you could draw a diagonal line here, but that doesn't really work. If you flip over, let's say I take this point here, take that point and jump over that line, it will not end up down here. It's going to end up somewhere up here. So that diagonal line is not a line of symmetry. So we have two lines of symmetry for a rhombus or a parallelogram. On my paper, it looks like a rhombus. On this, it looks a little bit more like a parallelogram. Actually, it's the same either way. On the Saints logo, we have one line of symmetry straight down the middle. You can see each point has a matching point on the opposite side. This third one is a regular pentagon, which means that all of these sides are congruent. So for however many vertices we have, or however many corners we have here, we're going to have that many lines of symmetry. We can draw one through each side and the opposite vertex. This is always going to be true of regular polygons. Regular just means that they have all the same size sides. That means all the sides are congruent. And a polygon is really just a closed shape. So that has 5. Oops, I forgot to write that. The Saints logo has 1. This pentagon has 5. This last one's just an example of how this is true in nature also. That line of symmetry straight down the middle splits that butterfly, and it maybe is not exactly pattern-wise, but each point does directly have another point on the opposite side, so that is one line of symmetry. Alright, you should be able to try these example problems on your own. Try drawing each of the lines of symmetry. A vertical axis of symmetry means straight up and down. Horizontal means straight left to right. Alright, rotational symmetry is true if the pre-image and the image are the same after a rotation. The symmetry can be described by the angle of rotation. So however many degrees we can rotate it and end up with the exact same shape, that's an angle of rotation. That's an angle of rotational symmetry, really. Alright, so by what angles, 360 or less, do the following figures have rotational symmetry? So this Z, if you rotate it 90 degrees, that's 1/4 turn. That's going to end up on its side. So that's not a rotational symmetry. But if we keep going and flip it upside down, it's going to look exactly the same. So we can rotate it by 180 degrees and end up with the exact same Z there. We could also rotate it by 360. That's going to be true of all of these. If you rotate it by 360 degrees, it ends up exactly where it started. So that has two angles by which we can rotate and end up with the exact same shape. The recycling symbol. I'm going to actually keep going. Oh, no, I'm just going to go with the arrows. From there to there, then there to there, then there to there. That would be 3 rotations, 3 even rotations to create 360 degrees. 360 divided by 3 equal rotations means we can rotate it 120 degrees, and then another 120 degrees, and then obviously another 120 to end up with the exact same shape. So 120, 240, or 360. We have that regular pentagon again. So we can go from this point to that point, rotating once, there to there, rotating a second time, there to there, rotating a third time, there to there, a fourth time, there to there, a fifth time, to get back to where we started. So it's 5 equal rotations that take us 360 degrees. So 360 divided by 5, that means each of these is 72 degrees. So 72 degrees moves it over one spot. 144 would move it over 2 spots. 216 is 3. 288 would be 4, and then 360 ends up back where we started. The Saints logo doesn't really have any rotational symmetry besides the arbitrary one of 360. Alright, so you can describe a rotational symmetry by the angles. And actually that's going to be related to the idea of the order of rotational symmetry. I guess that's the second vocab word that we're talking about here. So we have a couple of vocabulary words that we have to be familiar with. Point symmetry means that it has symmetry by 180 degree rotation. So this one does not have point symmetry. There's no 180 degree rotation. That one doesn't, that one doesn't, this one does. If you can flip a figure upside down and end up with the exact same shape, we say it has point symmetry. Really, the word point there refers to a point directly in the middle by which each one has an exact opposite point on the other side. So there's a point directly in the middle where you could just flip it directly over there, from there to there, sorry, there to there, and end up with the exact same point on the other side of it. The last vocab word we have to be familiar with is the word order. The order of rotational symmetry is the number of times a figure has rotational symmetry within 360 degree rotation. So this has an order of 2. 2 angles within 360 degrees that we can rotate it by. 1, 2, 3. 1, 2, 3, 4, 5. And that's just 1. So everything has an order of at least 1 because you can rotate it 360 degrees. And however many more we have within 360 degrees, that's the order of rotational symmetry. So here we're going to state the order of rotational symmetry for each shape. A square, it's a regular quadrilateral. We could rotate it by 90 degrees, 180, 270, or 360. That is 4 rotations that we could possibly use to get the same shape. So this is a regular 4-sided shape, and it has an order of 4. A regular 40gon is just saying we have a shape that has 40 sides. I'm not going to draw all 40 sides, but it's got 40 sides, and they're all the same length. I'm obviously not going to be able to draw that, but it's the exact same idea here. We're going from one vertex to the next, from there to there, there to there, 40 times. That has an order of 40. We have a rectangle with an X through it. If I rotate this point 90 degrees, it would end up standing up on the short side. That's not going to be the same. But you can rotate it by 180 degrees. We can go all the way around to 180 and it end up back on its longer side. So you can rotate it 180 or all the way around for 360. So it has an order of 2. The last one's called a pentagram. It's a pentagon, regular pentagon, with a star in the middle. I can go from there to there, rotating once, really rotating 72 degrees to end up with the exact same shape. 2 times, 3 times, 4 times, from vertex to vertex. You can rotate 5 times and end up with the same shape. It's really the exact same angles as what we saw there. Alright, again, you got some practice. Should be able to figure out the order of rotational symmetry for each of these, and then which ones have point symmetry. Again, that's just by 180 degrees.